All right, everyone. So welcome back to the second session of today's tutorial. And we are very fortunate to invite Professor Mahdi Dolati from the Sharif University of Technology in Iran. So he will give us a talk on how the programmable network will help the video streaming. So let me briefly introduce the Professor Dolati here. He received his PhD in the computer engineering in the University of Tehran, and his research focused on the design and measurement of the programmable and software-defined network to support the network-oriented applications, such as not only video streaming, but also like distributed machine learning and so on. He has also had a lot of experiences in developing the network simulators, resource allocations, virtual networks, SDN, and so on and so forth. So he is also now leading a team of graduate students conducting research on the next generation networking systems. So Mahdi, are you online?
Hi, Zilly. I can hear you, and thanks for the introduction.
Perfect. So now it's your time to deliver the talk on the programmable network for video streaming.
I have prepared a video to present it offline in case that my internet is unstable. I'm wondering if you have received the link
Oh, right. Let me
from
check.
Farzad.
Can you send the link again to me
Okay,
on
sure.
the Zoom chat? Because further, are you still here? No, further is not here.
Oh, I see. In case it is very hard to um, do the video offline, I can present it myself, but let me send it first here.
I see.
Another better solution might be if I.
Right. Probably in that case, I can play the video.
Can I help? Is there any problem?
No, not.
Okay.
Great. Let me just play the video provided by Mahdi. Mahdi will be available later for the QA sessions, right?
Yes, I'm available, but I just send the video because I'm not sure if my internet will be good for the entire of the presentation.
Okay, great.
Thank you.
Let me share the screen. I'm not sure if my PC audio is shared. Let me check. Yeah, share computer sound. Great.
Hello, and welcome to my talk as part of the half-day tutorial.
Is everybody able to hear that?
I had the audio.
Okay, perfect.
Video streaming.
Okay, thank you.
AI-assisted coded-network coordination. In this talk, I will talk about programmable networks for video streaming. And here I would like to thank Farzad, Zili, and Abdelhaq who had talks before me. I'm doing this part offline to ensure that the delivery is smooth and there is no interrupt in my delivery. I would like to start the presentation with my agenda in this presentation. First, I will do an introduction and present a taxonomy of the area that I am targeting in this talk. Then I will talk about several current works that both are can be considered state of the art, and also they can be inspiring for to direct the future lines of research. And I will talk about some extensions and possibilities for future research, and I will conclude the talk at the end. My talk considers the combination of two emerging and very important topics: programmable networks and video streaming. Programmable networks have received a lot of attention in a networking community, and it's growing and becoming a powerful tool to enable next generation network services and systems. It is started by the advances in controlling the networks in a softwareized ways, and then by the capabilities of designing programmable data plane. And currently there are many technologies like P4 and eBPF to bring the programmability into the core of the network and also the edge of the network. These are considered some programming tools that are very interesting, and their success has fostered later research that enabled to bring newer and more powerful APIs into the network that allow different entities, different parties to make their effect into the network. These APIs can be divided into two different levels: the low-level APIs and high-level APIs. At low level, there is a new concept, the X apps, that is developed by ORAN Alliance, that allows for example, content delivery networks to control the radio bandwidth in the cellular networks at very fine granularity and near real-time time scales. And it's a very powerful tool to bring QoS on demand for different applications. And also there are efforts by Linux Foundation, as in the project Camera, to introduce standardized APIs that different applications can use to bring programmability into the realm of their application and use them for their benefits in a standardized and open manner. It basically bridges telecom operators and application developers and allows them to control the network in a ways that was not possible before. And on the other hand, video streaming is witnessing a considerable growth, and new applications of video streaming require further quality of service requirements, lower latencies and higher bandwidth. For example, different versions of virtual reality, as reported by a paper that I mentioned here, show that the acceptable latencies can vary from 10 milliseconds to 5 milliseconds, and the bandwidth must be at least 100 megabits per second, and it can rise to several gigabytes per second. When we put these two applications together, we see an opportunity here that we can use the network, a programmable network, to address the needs of the modern video streaming applications. So I would like to group the possible directions and current studies into several categories in order to explore them better, and with a clear view into the field. Um, one area, one category is the collaborative methods. By collaborative, I mean there is a signaling between the application layer, the video streaming layer, and the network layer. And this collaboration can be unidirectional or bidirectional. In the unidirectional case, the collaboration can be application aware networking or network aware streaming. By application aware networking, I mean the application sends a signal to the network, and the network uses that in order to do the forwarding and routing better in order to account for the application needs and application conditions. In network aware streaming, the application collects data from the network, more details from the current state of the network in order to adjust its decision making. In the case that there is no collaboration, I call these works isolated methods. These works are basically confined in the network layer and do not need a message passing between the application layer and the network layer. On the right, I have presented a illustration of this concept. We can see that the network can send informations like queue length to the application layer. An application layer can send information about quality of experience to the network, and this exchange of information can help both to make better decisions. Or the network can collect information from the request and response as they go from the server between the server and client of video streaming, and use them to make better decisions without directly contacting the application layer. And in this case, it would be an isolated method or completely in-network method. And each of these categories has its own benefits and drawbacks. Basically, when we have a collaborative method, we have to deal with a slow exchange of information from the application layer to the network. And as we increase this collaboration, the problem that we should solve becomes more challenging, because different parties are involved, and different parties with competing interests can make the decision making very complex. On the other hand, when we have isolated methods, we have limited information. These methods can be very fast, but they have limited information, and they may make very suboptimal decisions. So finding the best balance between these methods and finding the right architecture is very interesting field of research, and there is no definite answer to this question. Now I explore some of the works that I think can be considered the representative of each of these categories. The first work done by Tran et al. That I have put a reference here, they use the project camera and the X apps to improve the quality of experience of video streaming by using the quality of service, by controlling the quality of service by sending information through CMCD to the CDN, and the CDN, the content delivery network, to control the amount of bandwidth that allocated to the video streams, and help them when they are experiencing lower quality of experience. And their results show a clear improvement when they use this method. Um, the simple method that they have adopted is based on the buffer length. So when the buffer length becomes very low, they define a threshold here, BL min. They request a boost. They ask the network to give higher bandwidth to that stream. And when the buffer length exceeds a threshold, they withdraw that boost and they no longer need that high bandwidth. The picture on the right shows that as on the top they ask for a high bandwidth, and on the bottom they ask for a medium bandwidth. And we can see that um, when there is no boost, the stall is high and average bitrate is low. But as they request higher boosts or a higher bandwidth, they can lower the stalls and increase the average bitrate. But another interesting observation here is that um, the higher the bandwidth, it doesn't mean that the stall is lower or bitrate is higher. When you give a boost to the application temporarily, you have to take it back, and this um, change in the bandwidth that the application gets can actually damage its quality of experience. So giving a medium level of bandwidth to the application can be more beneficial, as the plots here show. Another interesting work in this area that uses the information from the applications to do the networking better is Autoplex here. And it uses information, the quality of experience information from different users to adjust the congestion control parameters of all the users. Autoplex is based on an interesting observation. They conducted a large scale measurement on more than 800 million live streams, and reached to this conclusion that users that can be grouped together, for example, users that are in the same ISP, for example, um, those that have a good quality of experience have the same parameters for their congestion control. So if we can somehow collect this information from users that have a good quality of experience, we can use those parameters and give it to the other users in order to control their networking. And it clearly shows a connection between the application and network, and it allows the network to behave better by knowing some information from the applications. Next, I explain another work that's done by a group that I am also part of it. From the network aware side of the taxonomy that I presented. In this work, we observed that we can collect information from the network and make decisions faster than relying on the ABR algorithm to find out and adjust its current situation. In this plot, we can see that as the buffer length grows, we can make a better decision, quicker decision at adjusting the decision of the ABR and select a better bitrate for our video. Based on this observation, we created an algorithm called CABR, the Congestion Aware Adaptive Bitrate Algorithm, And we tested it in a very small scale test bed that is presented here. And CABR works on top of the existing ABR algorithm, and it tries to adjust their decision based on information that it gets from the network. Basically, a programmable network sends its buffer lengths to the application, and the application works by using several thresholds here. When the buffer length inside the network is low, so it can actually increase the bit rate, and if the buffer length grows, it can lower the bit rate, the quality that is requested by the ABR. And we created artificial congestion inside the network and observed the effectiveness of this simple idea, and showed that we can use P4 and eBPF to create a meaningful connection between the network and the application layer. And our results show that the quality of experience clearly increases by using several representative ABR algorithms, and when we compare it with the case that CABR is completely disabled. And this plot shows that when CABR is deployed, we are able to avoid very bad situations that happen to the video streaming, as we observe stalls. In the case when CABR is not deployed, compared to the case where the CABR is active, and we are able to avoid stall in our experiments. Next work that I would like to discuss is in QoE. It's in the category of isolated methods. It's a completely in-network algorithm method that consists of two parts. One part monitors the flows, and the next part acts upon the results of monitoring. For monitoring, there are many options, for example, latency, packet loss, and other metrics. And here in QoE does an evaluation on interpacket gaps. And when the interpacket gaps increases and exceeds the threshold, they use priority queues in order to help the flow perform better. And this is very, again, simple solution that shows the potential of this kind of methods, and shows that the network alone can use its programmability to help video streams and increase the quality of experience. And their results here shows that when they use this in QoE methods, when they monitor the flows and optimize their quality of experience, they are able to achieve higher throughputs, as shown by the blue line here, compared to the red line that shows lower throughput for the flows that are not protected by in-QoE. And for the future directions that we can consider here, one area that I would like to talk about it is the use of sketches. Sketches have been around in the programmable data planes from its start. They are powerful data structures that allow using very limited resources in order to compute some metrics inside the switch, and they provide some performance guarantees, and using these sketches and adapting them for the quality of service and quality of experience of the video streamings inside the network can be an interesting future line of research. Another interesting line of research would be the use of in-network ML to protect and help video streams. Recent studies, as one that is presented in this slide, done by Zheng et al., show that we are able to put powerful machine learning models like binary neural networks completely inside the data plane. And they can address some questions like the selection of these thresholds that have been used in different algorithms to make their decisions. And they can help us to design data-driven solutions completely in network for better video streaming and higher quality of experience. In conclusion, here I talked about the network programmability and emerging open APIs that allow a higher level of collaboration between the network layer and applications. And we saw that we actually need this collaboration as the demand from the network increases and as the video streaming application require lower latencies and higher bandwidth. But the challenges here remain. For example, as we increase this collaboration, the decision making becomes more complex. How we can make this decision to be more closer to the optimal and avoid the problems that arise from this inherently distributed system. Another challenge that exists in this area is the limited resources inside the network. I try to address this challenge by introducing and referring to sketches, but as the need for more complex solution increases, we need to address this, and this is an interesting line of research. For example, using hierarchical solutions or solutions that use divide and conquer method can help us to tackle this challenge. Another challenge here is the malicious users and attacks that can be target this more collaborative architecture, and the solution to this challenge can be in network machine learning, because machine learning is capable of detecting anomalies and behaviors that are not expected and very hard to predict them before they arise. And we need pattern matching and other advanced methods to prevent them. So there are many challenges, but there are solutions here that we can explore and apply them to achieve better results. Here my presentation finishes, and I would like to thank you for your time, and I'm here to answer any questions that might be about my presentation. Thank you again, and have a good time.
Okay, thank you so much, Professor Madi. So are you online? Are there any questions?
Yes, Julie, again, thank you for handling the stream of the video. I'm here, yes, I'd be happy to hear any questions.
Right, probably I can begin with one simple question as well. So thank you so much for this great talk in a lot of directions of using the in-network ability to support video streaming. I'm just wondering because I mean, like probably many students might also ask this question. So from the internet architecture, so video is at the highest layer, right, the application layer.
Yeah.
In network handling are mainly like network layer and below. So how do you foresee the feasibility of doing that, let's say in a large scale production, or I mean large scale internet in reality?
Well, there are some APIs as I introduced them in the
Right.
first of
For
the
example, if you
presentation.
use Sketch or use some things that the video might be encrypted, right?
Yeah, and there are some proposals to detect and handle these encrypted streams too. But from other perspective, I think one part that you are referring to is these isolated methods that are completely inside the network. So they have very limited information and they have to handle these problems. Um, just detecting whether this is a video string or not and whether it needs some assistance or not is very challenging. You are right. And I think it's a very interesting area to target it. But on the other hand, the collaborative method, they use this information that comes from the users. And already some of these enterprise-related entities and standardization entities are proposing some solutions. So I think it is very feasible and practical, and probably we will see some of these in action to handle some of the bottlenecks in the network, um, especially collaborative methods, but those collaborative methods are slower. In the area of isolated methods, again, I think there are many challenges, but we need more research to address them and solve those problems.
Thank you so much. Would that just probably a quick follow-up? Do you think if that will break the end-to-end principle or end-to-end argument of the internet?
Um, Yeah, this is, if done right, I think we might tolerate it, especially now that these APIs are becoming available. Um, and the applications can ask the network, but still, I think this should be very carefully designed so that the network decides about the network. So maybe all the things that comes from the application are just suggestions, just informations and warnings, and this can help to keep the overall architecture stable. But again, this is very important aspect of this problem, both from decision making and resource allocation, and also the case for malicious uses that I refer to them.
Thank you so much. Any other questions from the floor? Okay, great. So thank you so much. So now let's jump to the next session.
Okay, thank you.
So,
Bye.
right, this tutorial today, we have, you can see from title, we have the expert from not only the network community, but also the codec community, which is also very important. So today we want to, we are very honored to invite Sergey as an expert from the codec community to give a brief delivery on what codec people think about as low latency video streaming questions. So let me do a brief intro to Sergey. Sergey is a technical expert of the Multimedia Technology Lab in the Huawei Moscow. So he received his master's degree in telecommunication networking. He has a long experience in the multimedia communication, including research and production on video, on audio, on AI, and so on. And most importantly, Sergey is also a very important author in a lot of patents and also scientific papers. Also, important participants of International Standardization Committee, as like today our second speaker, Abdel Bentaleb was talking about, right? The standardization is also a very important procedure in the long-term run of the Codec-Network coordination. And he has already contributed to the development of many video and image compression standards, such as H.266, MPEG-5, JPEG AI, and so on. And currently he is leading the video and audio compression team and co-chairing the ultra low latency packet loss resilience ad hoc group in the JBET. So today he will give us a talk on the ultra low latency communication and video standardization activity. So let's welcome Sergey. Now it's your time. Sergey, we cannot hear you. Looks like your microphone something has some problems. Can you try to plug and unplug? You're not muted, but we just cannot hear you. All right, let's just wait for a moment and for Sergey set up from this side. So usually the reason why we have this special guest today is usually in the network community, like SIGCOMM, we have a lot of talks from the perspective of the network people. But as a video streaming, as an intersection between the computer network and also the video codec people, it's also very important to see or to at least hear about the ideas from the other community to see how they think and how they value the research directions in this intersection area. So that is why we decide to invite the expert from the looks like we still cannot hear you. Can you try to just use the microphone from your laptop instead of the headset? So Sergey, in the down left, there is a part to select which microphone you can use in the audio. Can you try to switch to the other?
Testing, testing. Can you hear me now?
Perfect. Now it works.
Oh, perfect. Now,
Thank you so much, Sergey. Now it's your time. Can you share the screen?
what
Oh,
about?
yeah, go ahead.
Good, good. Sorry for small technical problems. Let me share my screen.
Thank you so much. Yes, we can see the screen. Go ahead, please.
Right. I hope you can see it now. Thanks for introduction, Professor Mann. Yes, today I would like to talk about ultra low latency video communication and what is going on in the video standardization activity. I will skip the introduction since we already have a perfect one. Here's the outline of my talk today. So first of all, I would like to introduce what people are considering under ultra low latency requirements towards the development of new standard like H.267. Then I would like to give some in deep details analysis about the problem of ultra low latency communication, and then overview of what is going on in standardization community called JVET activity. If you know, the JVET calls stands for Joint Video Exploration Team. And there is some potential solution evidence for ultra low latency communication, which I would like to introduce and discuss today with you. All right, first of all, if we are talking about the ultra low latency application, what we are considering under that. From a perspective of standardization, basically there is some discussion. What is ultra low latency? What is the border between the low latency, ultra low latency? From perspective of several companies and several standardization experts, if I'm talking about the ultra low latency, we are considering highly interactive video applications like cloud gaming, or maybe a virtual desktop infrastructure, also maybe stereoscopic 3D projection and metaverse reality. So basic idea, we have some interaction with the videos. We are not just watching it, like in traditional video on demand scenario. We're giving some input to the system, for example, like a cloud gaming. We give input, we send our like mouse, keyboards, events to the cloud server. It adjusts the like 3D scene in the game, render a new video and send to our client. And between these two events, the input and the receiving video, there is some latency, and this latency is critical for user experience, right? That's what's the critical parameters to have enjoy all of the game. And the typical numbers we are discussing now here, something about, I would say there is some consensus point or something about 50 milliseconds. For comparison, for traditional video conferencing, the good latency is like 150 to 150. Let's say for interactive video application, we have to decrease the latency significantly. And here are some challenges. I'll come to that a little bit later. What is going on in JVET standardization community now? Basically, in the past year, in 2024, there were several people currently discussing what the requirements for the next standard. In the past years, there were several contributions from different companies, including my one from Huawei, also from Nokia, from Tencent, from InterDigital, and many other companies. People emphasize that there are some market segments which are growing faster than traditional video on demand, like interactive video applications like cloud gaming and VDI. And new standard, in fact, must support such scenario because we have a lack of such support in the past, and past to standard like H.266, H.265, people didn't consider that part so much. Now maybe it's time to have a closer look to that requirements. In the beginning of this year, in January of 2025, there was a very good and big workshop organized in Geneva, in Switzerland, by ITU, jointly by ITU and ISO. And that workshop about the future video coding attracted a lot of people. Basically, 400 people participated on site in the big room and also 300 online. And several experts from the industry gave their talk, introduced the requirements and expectation from industry perspective for a next generation video standard. Namely, experts from China Mobile, from Amazon, from Samsung, from May Concept, who provides encoder optimization and knows the markets quite well. Several important inputs were delivered to standardization community. Maybe the important conclusion that compression ratio itself cannot be the only goal for the next standard. Let's say another 40%, 50% reduction of all bit stream is good, but it will not bring us some very, very new services or new quality. So this market is more or less stable. If we want to touch some market which is emerging and developing faster, we should consider in other aspects, like low complexity and low latency. These 2 points were mentioned in every report from the industry experts. For complexity, people a little bit concerned about the price for the chip area size for encoder complexity. Deployer needs to pay for it to take the compression efficiency advantage. And all of the reporters mentions low latency application as one of the key requirements for the new standard. Likely at the same, there was a collocated media JVET meeting in Geneva at the same time, and during the meeting it was some proposals, including proposal from my company, also from Tencent, who emphasized the necessity of starting the work on low latency in JVET. And based on those contributions, there was a ad hoc group dedicated to low latency and packet loss resilience established. And mandates of this group was to investigate let's say, whether there is a possibility to give some significant improvement on top of existing standard technologies to better support low latency video communication services, identify the test condition, test procedure, create some practical simulation software. Let's say, let's make it more practical and say established work to support these requirements. So quite many companies joined this activity. You can see like Huawei, of course, Tencent, Nokia, Sharp, Ericsson, LG. So people are interested in these activities. Let us see what's going on now. Maybe first of all, let us have some in deep detail analysis. What is the problem here, right? So we all are like video communication expert. I will just briefly remind that in real-time video communication, normally we have a sender receiver network in between, and we have the like capturing and video encoding. Then we have packetization. We send the packets to the network. On the receiving side, we depacketize and send it to video decoders, then finally render. And if there is some issue in the network transmission, we'll observe something like video stalling. That's maybe quite a common experience we faced maybe during the COVID time. If you remember, like a couple of years ago, all of us started using RTC real-time communication systems more and more. And I would say many of us face the problem with video quality, with audio quality, as the network was not so perfect, frankly speaking, as we expected before. And personally, from my personal experience, I just stopped using Wi-Fi in my home connection, switched back to good old cable connection when I joined some RTC calls, because network problems were too high to enjoy the good experience of the service. Let us see in the details what is going on behind the high-level architecture. So normally, if you consider real-time communication systems, for example, like WebRTC or many others, the principles are the same. So we have some video encoder and we have some channel estimator, right, which use some feedback from receiving side to predict the channel capacity, channel behavior, and based on this information, it controls a video encoder. And so our encoder generates our packets, we send it through some network. Maybe Wi-Fi connection is one of the typical for home and office usage. And finally, our packets are stored in jitter buffer to compensate network delays, jitters. And out of that, we can collect the packets, construct free payload, and put it for the decoding. Finally, we can render it to the display. That's the overall scheme, but if we look into details, we can find some typical problems. Orange blocks I mark here to emphasize some typical problems for each part of this communication stack. For example, channel estimation is a kind of hard problem. It's hard to expect the estimation can be done accurately and fast enough to be adapted to fast change of the network. Wi-Fi connection is a kind of, like every wireless channel, it's can be influenced by many other, let's say, interfering points who may try to access the same wireless channel. That brings some rapid channel fluctuation and interference. Because of that, the channel may change significantly and maybe experience some packet loss and packet delay. And jitter buffer is, we have to introduce a jitter buffer to compensate all these network issues. But the jitter buffer means delay, right? Any buffering on the way introduce a delay, in turns it brings us additional latency. In an ideal situation, we would just like to remove this jitter buffer or keep it as small as possible, but it's quite difficult to find a good trade-off between buffer size and buffer underrun possibility. For decoder side, another issue is that in general, decoder, at least if we stay in the standard, cannot decode the partially received information. If at least one packet from the slice is lost, we have to drop all the slice. And then we break the prediction chain, so it's kind of, how to say, problem for standard decoder. To compensate that, we have two options. either we will need to wait for transmission of the lost packets, but that will bring additional latency, of course, or we have to use some packet loss concealment procedure, which is in fact is not part of the standard. So it's vendor specific. If you are deploying some service, you cannot rely on the behavior on this procedure. Let's say you cannot be sure about the quality of your service. That's a kind of issue for the current setup. Let us look a little bit more inside about the channel behavior and what exactly is the problem. For example, here on the plot, the orange curve is the channel capacity. For example, we pick a Wi-Fi channel, evaluated every 16 milliseconds, which corresponds to every frame distance between two frames and 60 FPS. So you can see that average channel capacity is quite high, like 70 megabit per second. If we consider some sequence, average bit rate of that sequence, coded sequence, video sequence, is like 25 megabits per second, 3 times less. So average capacity is fine. So we should expect that our video will be delivered without issues if we just make a simple measurement of matching between the codec bit rate and the channel capacity. Everything should be fine. But if you have a closer look and make this, let's say, fast measurement of the channel, we can observe that fluctuation is very, very significant, right? So it's sometimes the instant channel capacity falls below the codec bit rate at the current frame. That means that this part of the video will be delayed. So if we have enough latency on the next channel opportunity, we will deliver current frame and the past frame, no problem. But if our latency is restricted, we will observe some late packet from the receiving side. That will bring us some problem. Here is some demo. Let me try to play it. Yes, like that. For example, on the left corner, hope you can see it through the Zoom. Left corner, a video played on, let's say, clean channel without any restriction on the latency. Top right corner, we put some restriction on the downstream latency, like 16 milliseconds. We can see that sometimes video become like frozen because some packets were not delivered in time. If we increase the latency to 50 milliseconds, the video is more smooth. 100 milliseconds, almost no problem at all. So that means that latency, in fact, depends on the video quality. In fact, depends on the latency we are putting as a restriction for the transmission side. A few words about the packet loss. Of course, we know there are packet loss, and then in Wi-Fi scenario, it may be quite significant. Sometimes the peak packet loss may be up to 90%. However, the channel packet loss in most cases can be solved by retransmission at the channel level. For example, Wi-Fi has some logic in the protocol which tries to retransmit the packets until the packet lifetime is not over. So basically, I would say for packet losses, the problem is not that high, even for wireless connection. The biggest problems for our analysis is packet delivery time or packet late ratio. So on the same channel, we measured the packet loss ratio for 60 millisecond restriction again, and we observe that peak ratio sometimes comes to 100%, and the average ratio is also quite high, 8%, which is quite big number for standard decoder. And if we experience different latencies, like on this picture, of course, with increasing latency budget, the overall ratio is decreased. For example, in this scheme, we experience 4 different latencies, 16, 24, 32, 50. And you can see that peak and average numbers are decreased depending on with increasing of the latency budget. So the main conclusion that most of the problem in low latency communication scenario for video decoder are the late packets. Latency restriction to the system directly influences this value. And decoder have to deal something with that. And based on that concept, inside of JZ core group 18, the number of this core group on ultra low latency, there was some simulation software established and maintained, and repository software is available for all Impact members. So basic idea, the software was based on VVC reference model, which is called VTM, is a normal reference model. It contains H.266 encoder and decoder, and two elements were introduced, network model and jitter buffer. So the network model reads some packet trace files. Basically, the bitstream we obtain for encoder from encoder is chopped on packets of standard MTU size. And the packet trace files were obtained from a network simulator called NS3, is quite popular simulator for the channel research guys. So we modulated some physical typical room, like small or medium-sized home and office. There is active access point, a station is moving with walking speed, and there is an interfering room close to the main access point, which brings some interference, so there's some downloading some traffic. And modeling this physical room, we run the NS3 simulator and recorded packet trace files, and these packet trace files are used for network modeling. And for jitter buffer, we can set different latency restrictions. For example, on the current experiments people doing in JVET is like for numbers. So we can run experiment, we can run encoder, decoder, simulate the network with different latency restriction, obtain some quality metrics. On the right side, there are a list of such metrics. Maybe most important are the average piece an hour or average quality metrics, also freeze ratio or stall ratio. And in some experiments, people also controlling worst case piece an hour frames. Basically, this is like 5 or 10% quantile of the picture reconstructed quality distribution. So once we have conducted the experiment, we can build the curve. For example, for different latency restrictions, like in our experiment, we can put on the chart some average reconstruction quality, and there will be some curve. Then we can compare two solutions and measure the average distance, and for example, PSNR, and put it to the single number corresponding to some test case. Like for give an example, like for a cactus. This is the current test environment people are experiencing in JVET. And maybe latest news of latest JVET meeting that was held in July in Daejeon, Korea. There was a contribution also from me and my colleagues from Huawei, which illustrates some evidence of potential technology which can be used on top of existing H.266 standard to give some advantage and improvement in the ultra-low latency scenario. So using the based on the test environment of ad hoc group and using the methodology discussed in this ad hoc group, it was demonstrated that for low latency restriction scenarios, on average, like 2.2 dB of improvement can be achieved if you compare existing scalable coding H.266 with some enhancement, which will be introduced on the next slide. So that was to say kind of message or evidence showing to community that potential improvement can be achievable. Yeah, let me show you some example. I would not run the video right now. I would suggest you to go to the link and check the contribution. And there are some videos uploaded together with this contribution, also using some Google Drive. The basic idea that scalable solution, maybe you can see, if you lose at least one layer, one packet from enhancement layer, you have to drop all this information, all this layer from the decoding, and that will bring you some degradation of the video quality. Basically, you will have to use just a base layer, which in current experiment is bypassed without loss for simplicity. As a result, the picture will be blurred. Like this example. If you have opportunity to reconstruct from every packets you received, your picture will contain much more high frequency information. That's main source of average of improvement of the quality and that scenario. Few words about the design. That evidence. Basically, the design is based on existing architecture of H.266, 4, 5, so no significant change in architecture. Just 3 design elements were introduced. First of all, which is called data partitioning. Basically, it is known technology from H.264 and 3 times from that standards. Basic idea is splits information between prediction and residual on 2 independently coded bit streams. Like on this picture, prediction information goes to stream A and the residual information goes to stream B. Second modification was to introduce multiple chunks for residuals. So they're independently coded. So if some of them is lost, we can use another ones for reconstruction that give us more high frequencies in the reconstructed picture. It's a normal, we have several chunks, then we packetize, if packets are lost, like on this picture, some chunks are lost, but the rest can be used for reconstruction. Another, the third one modification was so-called lost-aware filter. And this is an N-based filter which takes error mask because we know the position of the picture of the errors. We can use this information to enhance the final output picture. And here is some example. For instance, on the left side, you can see some character sequence. Some information were lost. We use a motion compensated picture and compensated on this ceramics. You can see some block artifacts because we lost the residuals, but still some background from past frame can be used. And if we apply this lost-aware filter, these artifacts can be masked out and make it more smooth and pleasant for final display for the user. Another example, it's more, say, more extreme case, is fast moving. There are some drumsticks from the sequence called riddle dance, right? So some information is completely lost where I have a lot of square blocks, but if we apply filter, it tries to recover some information from surrounding delivery blocks. It's just quite helpful. Right, maybe the last point I would like to emphasize here that in this experiment, we use some transmission priority model to show how much user experience can benefit from so-called cross-layer design, let me call it like that. So we have some prioritization of the stream provided by encoder, and we use this prioritization to deliver most important information first, for example, like layer 0, which is base layer for scalable codec. In the initial experiment, we just bypass this information, but later on, people are currently experimenting with like disabling the simplification. And besides of layer 0, which is most important, we have different priorities and importance introduced by data partitioning for stream A and B and enhancement layer, and we can use this differentiation for further prioritization of the traffic. Another modification, the packet lifetime, which corresponds to Wi-Fi scenario, also 5G, they have the similar functionality. In current experiment, we have the packet lifetime equal to latency restriction. Basic idea, we don't like to send the information which is not needed anymore. So once we imagine, if we know the latency restriction of end-to-end application, we can use information to drop unnecessary in packets and to avoid the channel overflow. Yeah, that's it. So in the conclusion, I would like to emphasize that low latency requirements attracts a lot of attention and currently recognized as an important feature for future video technology business. So for standardization or for deployment. And for traditional scheme, which is based on traditional approach and separates source and channel coding, from current analysis, it is concluded that it may be difficult to fully satisfy the requirements. And some evidence were demonstrated that cross-layer design can provide some significant improvement of user experience, showing like upper bound. If we have some joint design from a source coding part, from channel coding part, what will be the improvement? So we have some evidence which we can use for further research activities. All right, thank you very much. That was conclusion of my talk. So if you have any comments, questions, please.
Thank you so much, Sergey. That's a fantastic talk. So are there any questions from the audience first? Right. Probably I can also begin with a simple question. So basically, from what I understand, is like the codec people can assume a extremely simplified network, like your Wi-Fi or anything like point to point, one single channel. So would you think that if you would more favor a simplified network channel, or you want to consider more complicated protocols like TCP, IP, UDP, RTP, and that stuff?
Thanks for the good. Yeah, that's a good question. Let me answer it on the simplest part. Of course, for real-time communication, so far people consider RTP protocol based on UDP.
Right.
TCP is considered like uncontrolled latency, so we cannot rely on that much. For second part of your question about more sophisticated model, this is a kind of balance we need to hold because, you know, in JBET community, people are not very experienced in the network part and the system part. To let people understand the situation better, sometimes we need to take some simplification in the network model. What people are asking here to have more diversity in the packet trace files. So far only Wi-Fi scenario was considered, but people are requesting about 5G, 6G scenarios, also far distance wired internet connection. That will be like a next step for network simulation in the standardization activity.
Right. So probably a follow-up is, do you think if it's possible, let's say, probably in the low latency, I mean, ultra low latency, we do not really need TCP, IP, or UDP, RTP. We do not need those upper layer protocols. We can just send the raw video content over the Wi-Fi, the 802.11 protocols.
That's a good question. Yes, that's also possible. But on the other hand, people care about the wider deployment. Of course, we can have some like proprietary protocol between sending and receiving device on top of Wi-Fi, or directly use some Wi-Fi features. That will be good the first step. But for generality, since the standard developed for the wider deployment for decades, I would hope, we should rely on massively deployed network protocols already, and consider the future perspective of the protocol development. Well, simple answer is yes, we can, but it's not like a main target for standardization community.
Thank you so much. That's a very good answer. Are there any other questions from the floor? Okay, great. So if you have more questions, you can also type in the Slack, and I will forward the questions to Sergey later after the meeting.
Sure.
So let's thank the speaker again.
Thank you very much for your attention.
Thank you. Right, so our last part of today's tutorial, this is a half tutorial, is a hands-on part, where Jiayang Xu from HQST will guide you to showcase on how to really use the AI-assisted video codecs and get your hands dirty. So Jiayang, are you online?
Yes, can you hear me?
Yes, perfect. Okay. Right, so let me do a brief introduction. So Jiayang is a PhD student from the HQST, works on the video communication. And today, the hands-on activity will be helping you guide through an open source repo called Grace. Grace is a paper from NSDA 2024. So huge thanks to the authors of the Grace paper, because that is a great paper that we think can be extremely a good use case to show how the loss resilience video codec with the help of AI can help with the low latency video communication. So now, Jiang, it's your time to 12:35.
Okay, I'll share my screen. Just share my. Can you guys see my screen?
Yes, go ahead, please.
Okay, then I'm going to give the tutorial on how to run the Grace as Ramon said before. There is a brief introduction of the GRIS, and the key point of this project is to use neural networks to encode the videos, and has a good performance, especially for the situations where the video packets are lost. And it's developed by the University of Chicago's GCAO research group. And the open source repo is listed as this URL. And how to run this code? Then the first step is to set up our own environment. We need to first clone this repo as URL is this, and we need to enter the GRIS project, and we need to also install the necessary dependencies like FMPEG and Ninja and Python. Here the FMPEG is a powerful tool for editing the video and audio files, and the Ninja is for compiling. The first command is to install the FMPEG and Ninja. And now we assume that we already have Python and Panda environment. So we just simply run this command to create a new environment from this YAML file, which is already provided in this repo. And the next step is to download the models from online, and we download from this link, which is also provided by the authors. And once we download it, we copy the path where we downloaded to our current workspace, and we enter the models directory, and we unzip this compressed file. Once we unzip these model files, we can see the whole structure as shown in the right figure. And next, similarly, we need to also download the testing videos. Here, the testing video is also available in this link. And once we download and unzip the whole video files, the structure is shown as, look at this structure. And we also need to use the index these files to specify which videos we choose to run for the different methods. And here we can take a look at what the index file is. It is just show the paths for different videos. And after we have all things done, like we have cloned the repo, and we have set up our own environment, and we download the models, and we download the videos. And next we finally enter the running stage. Here I can show an example in my local environment. Here, just have everything done. We have a GRIS project, and the first thing is to enter the GRIS testing environment, and we need to first run GRIS. We just copy the command and paste into here. And you can see after we press enter, it's just running. And here we can show that it runs the frame size or how to resize the image, since it will take a time. So we just simply terminate it to show that to save the time. And here is for running the GRIS. And next step is to run the other different methods. Also, sorry, here is what the results look like. The results are saved as in the GRIS results GRIS directory, and we can take a look at what the CSV files are. We can see that the column titles are size, PSNR, SIGCOMM', and loss and frame ID. You can take a closer look to this, and you can take a closer look into the code yourself to have a better understanding of what the specific matrix is, what the specific meaning of this matrix is. And similarly for like the previous step, we will need to run the other models. Here is about how to run the pre-trained AE models. And similarly, we need to copy the command from the repo on the repo, and we paste it and press enter. And it will also successfully run in the code. Then this showing this screen. And also just terminate it since it is already successfully. And the results are also in the CSV files, and the whole structure is similar to the previous one. And we need also to run the baselines, the H.265 and the H.264. And it is also the same steps. We copy the command and we paste into the terminal. Now you can see we will load these videos or some models, and we will recite this image and we just run the code. And also I'll terminate this command. And the final running command, or the results are also the same as the previous two ones. And we also need to run the final experiment. The final experiment is error concealment. And you will follow the same steps as before. Oh, here you can see that here is the kindly note, and you see that after running the previous step, I may have to restart my terminal. So before we run this command, I'll start a new terminal and enter the Grace environment and run this command, the error concealment. You can see that it already runs. Especially for this command, it will take a long time. So you better prepare for it. And I will simply terminate this command. So how we run this running this code is as I shown in, and the results are also the same structure. And finally, after you run all the above scripts, we need to sort all this stuff into the figures to see the results more clearly. And the repo already have provided a plot.py file to make the figures. So here we just plot the figures. Now we need to enter the results directory, and we need to run the plot.py file. And you can see that we will plot the files and the results. The result image will saved in the same folder. And what does this image look like? We can take a look. It shows the SM value of different loss rate, the first three images of different loss rate for different methods. And the last image is about the SM value of different frame sizes for different methods. And so I think that is the whole pipeline of running this all this open source code. And finally, this is to make an acknowledgement and to thanks to their fantastic work about the Greece, and also thanks to the author's kind support for this tutorial. And I think that's it.
Great. Probably we can wait for a few minutes and see. I just post out the links on the Zoom chat about the GitHub repo, about the Google Drives, and the testing videos. Probably gonna wait for another 10 minutes and see if the audience can follow the instructions.
Oh, okay.
Right, in case you did not hear all the links, I copy and paste and send them to the Zoom chat. You can copy and paste from there. All right, so I guess Jayan will also be on site in Coimbra in Portugal for the next several days. So if you have any more questions in setup or in understanding the code, you can also try to find him later. So if there are no more questions, that is the end of this tutorial, this half-day tutorial on the video codec and network coordination. Thank you so much for attending, and wish you all the best in the remaining conference program.
Thank you for the amazing presentations and also for, well, everyone's participation. Very good. Thank you.
Thank you so much.
Thank you.